Hey everyone, welcome back to RM Dev Hub. In this video, we're going to build a small to-do app using some amazing Rust technologies, including gRPC for efficient backend communication, HTMX for modern reactive frontend without JavaScript frameworks, Warp for handling HTTP requests, Cargo Workspace for organizing our Rust projects, SQLite as our lightweight database, Cargo Make to simplify running multiple services. By the end of this video, you'll have a fully functional to-do app that seamlessly integrates all these technologies. Before we dive in, if you want to support the channel, consider joining my Discord community to discuss Rust projects and more. Link in description. Supporting me on Buy Me a Coffee if you find my content helpful. Link below. Now let's get started. Let's start with setting up gRPC in Rust using protobuf. Let's get started. The first step is to create an empty folder and open it in VS Code. I've already opened my folder in VS Code. Now open the terminal because we need to install protobuf, which is essential for defining our proto files in gRPC. The installation command is different for each operating system. I've added the correct command for your system in the video description, so be sure to check there. If you are using Linux, then run sudo apt install protobuf-compiler. If you are using Mac, then run brew install protobuf. If you are using Windows, then need to install choco. After installing choco, you can run command choco install protobuf. Once the installation is complete, we can move on to creating our protobuf file for gRPC in Rust. Now we're going to talk about gRPC, what it is, why we need it, and how it compares to traditional REST APIs. Let's get started. So what exactly is gRPC? gRPC stands for Google Remote Procedure Call. It's an open source framework developed by Google that allows different services to communicate efficiently over the network. Unlike traditional REST APIs that rely on HTTP and JSON, gRPC uses protocol buffers or protobuf, which is a faster and more efficient way to serialize data. Now, why should we use gRPC instead of REST? Here are a few key reasons. High-performance gRPC is much faster than REST because it uses protobuf instead of JSON, reducing data size and improving speed. Bidirectional streaming, unlike REST, which follows a request-response model. gRPC supports real-time streaming between client and server. Strongly typed APIs, since gRPC uses protobuf. It enforces strict data structures, reducing errors and improving reliability. Cross-language support: you can use gRPC with many programming languages like Rust, Go, Python, and Java, making it perfect for microservices. gRPC is widely used in modern cloud applications, especially for microservices communication, streaming real-time data, EOT, and mobile applications, interacting with AI and machine learning services. So that's a quick introduction to gRPC and why it's so powerful. In the next section, we'll dive into setting up gRPC in Rust step by step. Now in section, we'll set up our Cargo TOML file for our Rust gRPC project and understand how Rust Workspaces work. Let's get started. First, let's create a Cargo TOML file. This file is essential for managing our project dependencies in Rust. Now let's add the required dependencies to our Cargo TOML file. Now, let's take a moment to understand what a Rust workspace is and why we are using it. A Rust workspace is a way to manage multiple related Rust projects under a single directory. Instead of handling dependencies separately for each project, a workspace allows us to share dependencies and build everything together. It is useful for code organization, keeping multiple Rust crates in one place, dependency management, avoiding duplicate dependencies across projects, faster build since dependencies are shared, compiling is more efficient. Now, let's break down the workspace section in our Cargo TOML file. Members equals. This tells Rust that our current directory is the only member of the workspace. If we had multiple Rust projects or crates, we could list them here. Resolver equals 2. This enables the latest dependency resolution mechanism for workspaces. It ensures dependencies work correctly across multiple members. In the workspace dependencies section, we define all dependencies once, and any project inside this workspace can use them. For example, our dependencies include Tokio asynchronous runtime for Rust, Warp web framework for building HTTP APIs, Tonic the Rust gRPC framework, Prost used for handling protobuf, SERD for serializing and deserializing data, SQLite a powerful SQL toolkit for Rust, Doten for managing environment variables. Tower HTTP provides HTTP utilities like CORS handling. Now, any Rust crate inside this workspace can use these dependencies without declaring them again in their own Cargo TOML files. So that's how you set up the Cargo TOML file and use Rust workspaces for better project management. In the next video, we'll move forward with writing our proto files and implementing our gRPC service. Now in section, we'll create a gRPC service definition using protocol buffers, protobuf. we'll define a to-do proto file that will serve as the foundation for our Rust gRPC service. Let's get started. First, let's create a new folder named proto inside our project directory. This folder will hold all our proto files. Now inside the proto folder, let's create a new file named to-do proto. Next, let's add the following code to define our gRPC service and messages. Now let's break down this file and understand what each part does. Syntax equals proto3. This specifies that we are using protocol buffers v3, which is the latest version. Package to do. This defines the package name, which helps avoid naming conflicts in larger projects. The to-do service defines 4 remote procedure calls, RPCs, that our gRPC server will handle. RPC create to-do request returns to-do. This RPC allows clients to create a new to-do item. It takes a create to-do request and returns a to-do object. RPC get to-dos empty returns to-do list. This fetches all to-do items. It takes an empty request and returns a list of to-do items. RPC update to-do request returns to-do. This updates an existing to-do item. It takes an update to-do request and returns the updated to-do. RPC delete to-do request returns empty. This deletes a to-do item by ID. It takes a delete to-do request and returns nothing, empty. Now let's go through the message structures used in this file. Message to-do represents a to-do item with 3 fields. ID, a unique identifier, optional. Title, the task title, required. Completed, a boolean indicating if the task is done. Message create to-do request contains only a title field because when creating a to-do we don't need an ID, it will be generated. Message update to-do request contains ID, title, and completed fields, allowing updates. Message delete to-do request contains only ID, since deleting requires just the task ID. Message empty, a placeholder message used when there's no request or response data. Message to-do list contains a list. Repeated to-dos equals 1, meaning it can hold multiple to-do items. Now that we've created and explained our to-do proto file, let's save it. This file will be used to generate Rust gRPC code automatically. That's it for this section. We've successfully defined our gRPC service and messages using protocol buffers. In the next video, we'll generate Rust code from this proto file and start implementing our gRPC server. Now in section, we'll create a gRPC server in Rust from scratch. We'll start by setting up our Rust project and preparing it to handle gRPC requests. Let's get started. First, let's create a new Rust project named gRPC to do. This will be our gRPC server. Open terminal and run the command cargo new gRPC to do. In the last section, we created our Rust project for building a gRPC server. Now let's move forward and add the necessary dependencies to our Cargo TOML file and understand their purpose. Let's get started. First, open our gRPC to do project in VS Code if you haven't already. Then open the Cargo TOML file. Now let's add the required dependencies. In the Cargo TOML file, update it with the following. Now, let's break this down into 2 sections: build dependencies and regular dependencies. Build dependencies are special dependencies used only during the build process. They are not included in the final compiled binary but help generate code or configure the project before compilation. In our case, we are using tonic build. This is required to compile our proto files into Rust code during build time. It takes care of generating Rust structs and gRPC service stubs from our gRPC definitions. Since this is only needed while building the project, it goes under build dependencies instead of dependencies. Now, let's go over the regular dependencies that are included in the final compiled binary. Tonic, the core library for implementing gRPC services in Rust. Prost, a high-performance protocol buffers library for Rust. It helps in serializing and deserializing gRPC messages. Tokio, an async runtime that helps handle concurrent tasks efficiently. SQLite, a Rust library for working with databases asynchronously. Dotemv allows us to manage environment variables using a env file for configuration. Cert, a serialization/deserialization library, useful for converting data between formats like JSON and Rust structs. TonicWeb enables support for gRPC web requests, allowing us to interact with gRPC from a front-end application. Tower HTTP provides HTTP utilities like CORS handling, which is essential when working with front-end clients. Awesome! We've successfully added and understood the dependencies required for our Rust gRPC server project. In the next video, we'll define our gRPC service using protocol buffers and generate Rust code from it. In the last section, we added dependencies to our Rust gRPC project. Now let's move forward and create a build.rs file at the root of our gRPC to do project. This file will help us compile our proto files into Rust code automatically. Let's get started. Before we write the code, let's understand what the build.rs file does. The build.rs file is a build script in Rust. Cargo automatically runs this script before compiling our project. We use it to generate Rust code from our gRPC proto files using tonic build. This means we don't have to manually write the Rust code for our gRPC services. This script does it for us. Now let's create the build.rs file at the root of our gRPC to do project. Now open build.rs and add the following code. Let's break this down step by step. fn main result boxed in std. Error this is our main function. It returns result boxed in std. Error meaning it either succeeds OK or returns an error. Tonic build compile proto to do proto. This compiles the gRPC proto file located in the proto folder. Tonic build generates the necessary Rust service and message definitions. Ensures that if an error occurs, it gets propagated instead of crashing the build. OK. If everything runs successfully, we return OK, indicating that the build script executed without errors. If everything works correctly, Rust will generate the necessary gRPC code from our proto file. Awesome! We've successfully created and explained the build.rs file for our gRPC project. This script ensures our proto file is compiled into Rust code every time we build our project. In our last section, we set up our build.rs file to compile our gRPC proto files. Now let's move forward and install SQLite, which will help us manage our database migrations. Let's get started. To interact with our database, we need to install SQLite. This tool helps us run database migrations, create tables, and execute queries. Now let's install it using Cargo. Open your terminal and run Cargo install SQLite. Let's break this down. Cargo install. This command installs a Rust crate globally on your system. SQLite. This is the SQLite command line tool which helps us manage our database. Now that we have SQLite installed, let's create our first migration to set up our database tables. SQLite migrate add create tables. Let's break this command down. SQLite migrate add. This creates a new migration file inside the migrations folder. Create tables. This is just a name for our migration. You can name it anything, but it's good to be descriptive. Awesome! We've successfully installed SQLite and created our first database migration. In the next video, we'll write the actual SQL code inside the migration file to create our tables. In the last section, we installed SQLite and created our first migration. Now let's define our database table inside the migration file. Let's get started. First, let's navigate to the migrations folder and open the newly created migration file. The file name will look something like this. Migrations /20,240,326,000,000 create tables SQL. Now, let's add our SQL code to define the to-dos table. Inside the migration file, add the following SQL code. Now let's break down what this code does. Create table if not exists to-dos. This creates a table named to-dos if it doesn't already exist. ID integer primary key auto increment. The ID column is our primary key and will automatically increment for each new entry. Title text not null. The title column is of type text and must always have a value. Completed Boolean not null default 0. The completed column is a Boolean true/false value. By default, it is set to 0 false. Awesome! We've successfully created our to-dos table. In the next section, we'll write Rust code to interact with our database using SQLite. In the last section, we created our to-dos table and ran our first migration using SQLite. Now let's set up our configuration file to manage the database connection in Rust. Let's get started. First, inside our gRPC to do project, let's create a new file named config.rs in the src/directory. Now let's open this file and add the following Rust code. Inside config.rs, add the following code. Now, let's break down what this code does. #derive debug clone. This allows our struct to be printed for debugging and cloned when needed. Pub struct config. This struct stores the database URL for connecting to SQLite. Impl config. This block implements a function to initialize our configuration. Pub-fn init. Self. This function creates and returns a config instance. SQLite //tododb. Mode equals rwc. To string, this sets the database URL to an SQLite file named tododb. SQLite //tododb specifies that we're using SQLite. Mode equals rwc. Opens the database in read, write, and create mode. Now that we have our config struct ready, we can use it in our main file to initialize the database connection. We'll do that in an upcoming section. Awesome! We've successfully set up our config.rs file, which will help us manage database connections efficiently. In the next section, we'll connect our Rust app to the database using SQLite and start writing queries. In our last session, we set up our database configuration. Now let's create the DBRS file, which will handle all database operations. First, I'll write the full code, then I'll explain it step by step. Let's get started. Inside our gRPC to do project, let's create a new file. Now let's add the complete code first. Now explain code. The to-do struct. This struct represents our to-dos table. ID option I64, the primary key which is optional because it's auto-generated. Title string, the task name required. Completed bool, a boolean field that marks whether a task is done. Init DB function. This function initializes our SQLite database. It checks if the database exists. If not, it creates one. If yes, it just connects to it. It applies database migrations from the migrations folder to ensure our tables are up to date. Finally, it returns a database connection pool for executing queries. Create to-do function. This function adds a new to-do to the database. It runs an insert SQL query with title and completed. It returns the new task, including its ID. Get to-dos function. This function fetches all to-dos from the database. It executes select ID title. Completed from to-dos. It returns a list of to-dos. Update to-do function. This function updates a to-do by ID. It modifies the title and completed fields. It returns the updated to-do. Delete to-do function. This function removes a to-do by ID. It executes delete from to-dos where ID equals. It does not return anything, but it removes the task from the database. Awesome. We now have our DBRS file handling database initialization and CRUD operations for to-dos. In the next section, we'll set up our gRPC server and integrate these functions to make API calls. In our last video, we set up our database operations in DBRS. Now let's build our gRPC server by adding the server.rs file. This will expose our CRUD operations over gRPC. First, I'll write the full code, then I'll explain it step by step. Let's get started. Inside our gRPC to-do project, let's create a new file. Server.rs now, let's add the complete code first. Now explaining the code, importing modules. We start by importing our gRPC module from the to-do proto file using. This allows us to use the generated gRPC service definitions. Defining the myTodo service struct. We define our service struct that holds a database connection pool. This will be used to execute database queries. Implementing the from trait, we implement from DB. To-do for to-do so we can convert database objects into gRPC responses easily. Implementing gRPC methods. Create to-do handles creating a new to-do, extracts request data, calls create to-do function from dbrs, returns the newly created to-do. Get to-dos fetches all to-dos and returns a list. Update to-do updates an existing to-do by ID and returns the updated to-do. Delete to-do deletes a to-do by ID and returns an empty response. Running the gRPC server. Finally, we define run server, which starts the server at localhost 50051, initializes the database, enables cores for cross-origin requests, registers the gRPC service. Awesome. We now have our gRPC server running and handling CRUD operations. In the upcoming section, we'll create a gRPC client to interact with our server. Now let's update our main RS file. This will serve as the entry point of our Rust gRPC server. Now open the main RS file inside the gRPC to-do project and replace its content with the following code. Now open the main RS file inside the gRPC to-do project and replace its content with the following code. #Tokio. Main this is an attribute macro provided by Tokio, which allows us to run asynchronous code inside our main function. Without this, Rust's main function wouldn't support async. Async fn main. This defines our main function as asynchronous. It means we can use await inside it, which is necessary for running async tasks like our server. Run server. Await. This calls the run server function, which we defined inside server rs. The function starts our gRPC server and keeps it running. The await ensures we wait for the server to keep running instead of instantly exiting. With this, our main RS is now complete. Now let's move forward and create our gRPC client with Warp and HTMX. Now let's create a new Rust project named HTMX Warp. This project will serve as our server using Warp for our gRPC client with HTMX. First, open your terminal and run the following command to create a new Rust project. Cargo new HTMX Warp. This command does the following. Cargo new HTMX Warp creates a new Rust project named HTMX Warp. Now that we've created our Rust project, in the next step, we'll open the Cargo TOML file and add dependencies for Warp, HTMX, and gRPC communication. Stay tuned. Now that we have created our HTMX Warp project, let's set up the dependencies. First, open the Cargo TOML file in your Rust project. Now let's add the following dependencies inside the dependencies section. Explanation of dependencies. Tokio, a sync runtime for handling requests efficiently. Warp, a lightweight high-performance web framework for Rust. Tonic, a gRPC library that allows us to communicate with our backend. Pros, a library used for encoding and decoding protocol buffers. Protobufs. HTMX, this will help us integrate HTMX in our web app for dynamic, real-time updates. Surd, used for serializing and deserializing JSON data. HTML escape, helps us safely escape or unescape HTML content. Next, let's add the following inside the build dependencies section. What is build dependencies? Unlike normal dependencies, build dependencies are used only during the build process. Tonic build, this compiles our proto files into Rust code during the build process. Now that we have set up our dependencies, let's move on to the next step where we will create the build.rs file and configure it for gRPC. Stay tuned. Now that we have set up the dependencies in our Cargo toml, let's move on to the next step, creating the build.rs file. What is build.rs? In Rust, a build.rs file is a build script that gets executed before compiling the project. It is typically used to generate code from proto files when working with gRPC and Tonic. Create build.rs inside the build.rs file, paste the following code. Let's break this down step by step. fn main, result, boxed_in_std. Error, this is the entry point of our build script. It returns a result type that can either be OK, success, or an error. The boxed_in_std error allows us to return any type of error. Tonic build, compile protos, /proto/to-do proto. This compiles the to-do proto file located in the proto/ directory. The operator propagates errors automatically. This step generates Rust code from the proto file, which will be used by our server and client. OK, this indicates that our script executed successfully without errors. Now that we have set up our Rust backend using Warp and gRPC, let's move on to creating the frontend for our HTMX Warp project. What are we doing? We will create an index.html file inside our src/folder. This file will act as our client-side UI for the To-Do app. We will use HTMX to send requests to our backend without needing a full page reload. Navigate to your project's src/folder and create a new file index.html. Inside index.html, paste this code. Let's break it down step by step. Doctype HTML, this defines the document type as HTML5. This includes HTMX, a lightweight JavaScript library that enables AJAX-like behavior without writing JavaScript. If a to-do is marked as completed, it will be struck through. Add spacing between to-do items for better readability. This is the main heading of our application. This form allows users to add a new to-do. HTMX behavior hxpost equals /todos, sends a post request to /todos. hxtarget equals #to-do list. The response will be inserted inside #to-do list. hxswap equals beforehand. New to-do items will be added at the bottom. HTMX behavior hxget equals /todos. When the page loads, it sends a GET request to /todos. hxtrigger equals load. This makes sure the request is triggered when the page loads. If everything is set up properly, you should see a To-Do app interface that dynamically updates using HTMX. Now that our frontend is ready, let's move on to building our Warp API routes to handle these requests. Stay tuned. Now let's open our HTMX Warp project and update the main RS file. This is where we set up our server logic to interact with our gRPC backend and serve HTML responses. What are we doing? Importing and setting up gRPC client using Tonic. Defining our app state to manage the client. Creating structs to handle incoming form data. Writing functions to render dynamic HTML using Rust. Navigate to your project's src/folder and open main RS. First, I write a full code, then I explain it step by step. Now explaining code. Mod to-do. This imports the gRPC definitions from the to-do proto file. Struct app state holds the gRPC client to-do service client, allowing us to make API calls from Warp. Create to-do form handles new to-do submissions, capturing the title field. Update to-do form handles to-do updates, including completed, tracks whether the to-do is done. Extra, a flexible hash map that allows additional form fields without explicitly defining them. Render to-do list, to-dos, and to-do, takes a list of to-dos and generates HTML dynamically. Loops through each to-do and calls render to-do item to-do. Render individual to-do items, generates an HTML template for each to-do item dynamically. HTMX attributes, a checkspot equals /to-do/id. Sends an update request when checkbox is clicked. Checks delete equals /to-do/id. Deletes the to-do when the delete button is clicked. Checks include equals name equals title ID. Ensures the to-do title is sent with updates. Dynamic rendering, if to-do completed is true, applies check to the checkbox and completed to the text. Uses to-do ID unwrap or 0 to handle cases where the ID might be missing. Now let's continue working on our main RS file. In this step, we'll add handler functions to fetch all to-dos, create a new to-do, update a to-do, delete a to-do. First, I'll write the full code, then I'll go through it step by step. Now let's break it down function by function. Fetching all to-dos get to-dos handler, calls the gRPC server to fetch to-dos, handles errors using map error, converts the to-dos into HTML using render to-do list, creating a new to-do create to-do handler, extracts title from the form, calls create to-do on the gRPC server, returns the new to-do as an HTML response, updating a to-do update to-do handler, extracts title and completed fields from the form, calls update to-do on the gRPC server, returns the updated to-do in HTML format, deleting a to-do delete to-do handler, calls delete to-do on the gRPC server using the ID. If successful, returns an empty HTML response to remove the item from the page. In the last section, we worked on setting up our Rust web application. Now, let's continue writing the main RS file by adding our main function and integrating gRPC with Warp. First, I'll write the full code and then I'll explain it step by step. Let's get started. Now I'm adding the main function where we connect to our gRPC server, initialize the to-do service client, set up our application state, define API routes, and finally start the server. Alright, let's break it down. Connecting to gRPC, we start with #Tokio, main to make our main function asynchronous. Then we establish a connection to our gRPC server running on http://150,051. We create a to-do service client using tonic, which allows us to communicate with the gRPC server. We define app state, which holds our to-do client, and pass it into a warp filter so we can use it in our handlers. Defining API routes, we define several warp routes. /todos, get right arrow fetch all to-dos /todos post, right arrow create a new to-do /todos /id put, right arrow update a to-do /todos /id delete, right arrow delete a to-do each route uses, and then to call the respective handler functions. We combine all routes and use warp, serve routes, run 127.0.0.1 3030. Oh wait, to run our server on port 3030. And that's how we complete our main RS file, by setting up the gRPC connection, defining routes, and running the server. In the next section, we'll test our API and see it in action. Now our backend with gRPC and frontend using HTMX with Warp is now complete. Now let's automate the process of running both services using Cargo Make. We'll set up a makefile toml file to simplify our workflow so we don't have to run multiple commands manually every time. Let's get started. First, we need to install Cargo Make. Open your terminal and run this command: cargo install force cargo make. Since I already have it installed, I'm not running this command, but if you haven't installed it yet, make sure to do so. Now that Cargo Make is installed, let's create a new file named makefile.toml in the root directory of our workspace. Inside this file, we'll define tasks for running our gRPC backend and HTMX Warp frontend separately, and then we'll create a task to run both in parallel. Now, let's break down what's happening here. Task: gRPC to do this task runs the gRPC backend using cargo run p gRPC to do. Task: HTMX Warp. This task runs the HTMX frontend with Warp using cargo run p HTMX Warp. Task: run both. This task runs both gRPC to do and HTMX Warp in parallel using run task. It helps us start both services with a single command instead of running them separately. Now, to start both services together, just run. This will launch both the gRPC backend and the HTMX frontend in parallel. And that's it. Now we have a simple way to start both our backend and frontend with a single command. This will make our development workflow much more efficient. Our backend and frontend are now up and running. In this video, we'll open the browser, go to localhost 3030 and see our HTMX frontend in action communicating with the gRPC backend. Let's test everything. Now open your browser and go to http://localhost 3030. Here, you should see the frontend UI we built using HTMX. It's dynamically loading data by making requests to our gRPC backend via Warp. Let's go step by step and test if everything is working correctly. And that's it. We've successfully built a small to-do app using Rust, gRPC, HTMX, and Warp. This project is a great example of how we can combine modern web technologies with Rust to build scalable, efficient applications. If you found this video helpful, don't forget to like this video to help others find it. Subscribe for more Rust and backend development content. Hit the notification bell so you don't miss any updates. Also, join my Discord if you have any questions or want to be part of our dev community. And if you want to support the channel, feel free to check out my Buy Me a Coffee page. Thanks for watching, and as always, happy coding.